I will focus on the freight transportation, and I will focus on modal shift in a times energy model. So times is an optimization model. And I will focus on two modeling techniques, endogenous and exogenous. So okay. This is the outline of the presentation. And so this research was done in a context. Okay. This research was done in a context where the freight transportation represented 16% of Quebec greenhouse gases emission. And as you can see on the right, we want to decarbonize. So we are right now on the red line, the reference scenario, and we want to attain the target scenario, target decarbonization scenario, so the green line. So we have no choice but to decarbonize the freight transportation sector as well. So what solution do we have right now to decarbonize the freight transportation? So we could have electric battery trucks that are like currently developed in the world and in Quebec. We could also have catenary trucks that are like developed for the horizon 2030. We could also have electric train, but in Quebec, all the freight products are mainly transported by trucks, so there is not so much like window for electric train. So as you can see, we have only technological solution. So what about the behavioral solution? So in the freight transportation sector, the behavioral solution would be a modal shift between heavy trucks and train. So this is the objective of this presentation, to present result of a modal shift using two different modeling techniques. So for that, we used the North American Times Energy Model, NATEM. So Times model, our successor of EFOAM and Markle model, and they are optimization models. So it means that they optimize a system at the lowest cost. There are also bottom-up models because they are very technologically detailed, and they go from a lot of technology to answer an end-use energy demand. And finally, they are partial equilibrium model because they focus only on the energy sector. This is like the global picture of the NATEM model we used. So as you can see, a lot of technology interconnected. But in this presentation, we will focus only on the transport energy demand. So for this presentation, I will present three scenarios. So the first one is a technological only scenario. So this is a decarbonization scenario where we attain the decarbonization using only the technology. And then I have two modal shift scenarios. So where there is a modal shift between heavy trucks and train. And this is done with two techniques, so endogenous and exogenous. And I will just explain in the next slide what is endogenous and exogenous. So exogenous, it means that this is a fixed behavioral shift, so a fixed modal shift scenario that is based on external hypotheses. So for example, if we say that there is a possible modal shift of 17%, then we can decrease the heavy trucks demand by 24% and increase the train demand by 6%. Of course, the hypotheses that we used in this research are a bit more complicated. And actually, they're from a study that has been done before in Quebec. And this study permits to disaggregate the different merchandise type and to show the possible modal shift depending on the type of the product. So we created an exogenous scenario based on this data. Then we have the endogenous modeling technique. So endogenous means that this is an optimized behavioral shift scenario. So basically what it means is that the model can optimize and can choose the shift that it wants to do by itself. So how do we do that? We create an aggregate demand that is the sum of the two component demand, heavy trucks and train. And to this demand, we add a variable step in which the demand can vary. So this is the own price elasticity. And the two components demand are also linearized and are a proportion alpha of the aggregate demand. And for each of the component demand, there is also an elasticity that is called substitution elasticity that is possible. So this represents like the possible modal shift that the model can choose. So this is a very technical slide, just to remember that the endogenous technique is done by introducing elasticity of substitution so that the model can optimize the modal shift. And the value that we use for the elasticity of substitution are from the literature, and we choose a minimum value and a maximum value. So now for the result, we can see here the useful energy demand. So these results are in difference with the reference, so the red line at the beginning, so the reference scenario. And you can see this is the demand variation for heavy trucks and train. On the left, it's the technological only scenario. In the middle, it's the exogenous scenario, so where the hypotheses are fixed externally. And on the right, it's the endogenous scenario, so where the model can optimize by itself the shift. So as you can see, if you let the model choose by itself, it does not switch as much the demand as if the shift is exogenous. We also tested a lot of scenarios with different levels of substitution elasticity just to see how the model would react and if it could like create a disruption equal to the one created with the exogenous technique. So as you can see in this figure, the model quickly reaches around a substitution elasticity of 0.6, an optimal model shift, and just stay like that, even if you increase the substitution elasticity. Then we can also look at the energy consumption. So this is the energy consumption for 2030 and 2050 for the heavy trucks. And this is always the technological only scenario on the left, exogenous scenario in the middle, and endogenous scenario on the right. So as you can see, the technological only scenario, of course, is the scenario that consumes the most energy. And you can also see that it invests in expensive and complicated technologies such as catenaries at a high level since 2030. The exogenous modeling technique, however, in the middle, permit to avoid investing in catenaries in 2030 and also permit to cut the energy consumption for heavy trucks by are in difference with the technological only scenario, because of course the technological only scenario is the most expensive scenario because you have to reach decarbonization with technology only. So as you can see, both modeling techniques, so both scenario exogenous and endogenous, permits to avoid $1 million per year. But this is the exogenous scenario that permits to avoid a lot more cost. However, this result is to be taken with perspective because the exogenous method does not take into account the cost of reducing the demand, whereas the endogenous method, the model takes into account, because it optimizes itself, so it takes into account this cost. So to conclude this presentation, here are the messages that you should remember. So firstly, introducing modal shift into technicals model allows for less expensive and more realistic solution. So as we've seen, a technological only scenario leads to investing early in expensive technology. And also we don't know yet if this technology such as catenary will be fully operational in 2030, for example. Secondly, in the context of decarbonization, the modeling choice is crucial. So as we've seen in the result, if you choose to model the same modal shift with two different techniques, it does not lead to the same result. So you have to choose your modeling technique wisely. And finally, the models are not designed to do radical scenario. So this point is specifically for the endogenous technique, because we've seen that the model does not make radical disruption by itself. And this is a paradox because often we can hear people saying that we have to integrate more and more behavioral variable directly into the model, but at the same time we are in a decarbonization context where we have to reach like super constrained level of GHG, and the model cannot are not constructed to design decarbonization scenario. So thank you for your attention, and we'll see for the question later.